All right, welcome everyone to this machine learning workshop. My name's Harsh. I'm looking forward to teaching all of you. So machine learning is a very interesting aspect in terms of coding and computer science. So this image does a very good job of just sort of overviewing what machine learning is for those of you who don't know. So mainly today, we're going to be focusing on these two aspects called supervised and unsupervised learning. So within supervised learning, we're going to focus on regression and classification. And these two methods can be used to solve a variety of problems. So for example, regression can be useful when trying to do weather forecasting or population growth predictions. And classification can be useful when doing image classifications or diagnostics. And on the other end, unsupervised learning, we're going to be focusing on clustering, which can be used for targeted markets or customer segmentation. These are just a few of the topics we're going to go over throughout this workshop. So we're going to focus mainly on supervised versus unsupervised learning. And within it, we're going to do linear regression, nearest neighbor classification, support vector machines, regression, loss functions, overfitting, regularization, with something I call scikit-learn, reinforcement learning, and clustering. So we'll just start off with a quick overview of what supervised versus unsupervised learning really means. So as you saw in the last image, it's sort of just two separate branches of machine learning. And this image just sort of simplifies that. So if we go from machine learning into each of the two segments, and within that, in unsupervised learning, there's clustering. Within supervised learning, there's classification. And within supervised learning, again, there's regression. So supervised learning. So we're going to be focusing on this segment to start. So what is supervised learning? So by definition, supervised learning is a task where a computer learns a function that maps inputs to outputs based on a data set of input-output pairs. So for those of you unfamiliar with machine learning, that probably doesn't make a lot of sense to begin with. But as we go on, I'll try to explain it as best I can. So a simpler way of putting those terms is through this image. So we feed the computer some inputs, which would be our data. It runs it through a process and then gives us an output or a prediction of an output. And this just is like a feedback loop that runs continuously. As we put in new data, it will give us new outputs. So mainly for today, the different methods and techniques that we're going to be focusing on will have to do with the process. So machine learning focuses on the process and how to make that more efficient, where the computer sort of teaches itself how to improve and makes the outputs more accurate when we're doing predictions. So for example, if we give the computer this data, which is a bunch of images of apples and then a few of cupcakes, we run that data through a machine learning model. And then we give it a new data set, which would be this orange cupcake right down here, which is unseen and unlabeled data. The computer, through this process, should be able to identify that this is a cupcake and not an apple, and put it into the same class as the rest of the cupcakes. So now we're going to be moving on to actual techniques that are used in machine learning, and more specifically, supervised learning. So the first one is known as linear regression. So there are multiple tasks under supervised learning, and one of those is linear regression. This is a task where the function maps an input to a discrete output. As seen on the right, the various shapes are the inputs and the position of the graph would be the output. There's a set line that separates two distinct categories. This can be more easily represented through a real world example. So if we just focus on this image right here, you can tell that there's two separate sorts of data. So the red circles and the green plus signs. So these, just like the last examples with the apples and the cupcakes, can be the two separate classes. So we'll just call these apples and these cupcakes just to simplify it. So these are our data points. Now we're going to introduce a new data point to the computer, which is represented by this blue star right here, and the computer does not know which data set it belongs to. So using machine learning and linear regression, the computer is going to give this new data point a set class, whether that's apples or cupcakes. So with linear regression, the main technique is setting a fixed boundary as represented by this dotted line to separate the two classes. So as so on like this X graph or XY graph, you can see that all of the apples and the cupcakes are on their separate sides. The computer recognizes that and builds a boundary between the two. So when the new data point is introduced, it knows which class it belongs to. So a real world example of this can be seen through weather. So given some information on humidity and air pressure for a particular day, that would be the input. The computer decides whether it will rain that day or not, the output. So the computer does this after training on a data set with multiple days where humidity and air pressure are already mapped to whether it rained or not. A distinct pattern can be seen on the graph, and the computer draws a strict linear barrier in order to determine whether it will rain or not. So just to put that into simpler terms through this image, we can look at the different data points, which are blue circles and red circles, and the white circle is the new data point we're introducing. So humidity on the x-axis, pressure on the y-axis. The other points that are blue and red are already like past days. So example, on a specific day, this was the pressure and this was the humidity. And then red, we could say it represented that it did not rain. And then on another day, this was the pressure and humidity, and on that day it did rain. So doing that over and over again and collecting data through multiple days, this graph can be made as like a data set. So when we introduce this new day, which could be, for example, we know tomorrow's pressure and humidity, the computer is trying to predict whether it will rain or not. So if we just look at this graph in general, and like I mentioned before, linear regression, the computer sets a strict linear barrier. So a barrier that could be estimated could look something like along the lines of just across this section. And then the new data set would fit in with the other blue circles. So just a line something like this would be the barrier. So issues with linear regression within supervised learning. So obviously, as we can see with this image, that not all the data points are in the right class. And this is because a set barrier does not work well with real life examples, especially rain. As you guys know, that some days it looks like it's gonna rain and it does not, and other days it's clear skies and suddenly it starts raining. So all of these are major issues that break down the usability of this model. But that's the entire point of machine learning, that there's different techniques for different sets of problems, and that we can use various techniques and see which one works best. So another technique that we can use is called nearest neighbor classification. So one way of solving a task, like the one we just described in the previous slide, is by assigning the variable in question the value of the closest observation. So what does this mean? So this means that measuring distance between the new point and the closest existing points, and using that distance to see which point is the nearest neighbor. This approach can be thought of as like a dartboard where your new data point is the bullseye, and you have to try to look at for other darts that are closest to that bullseye. So this can, again, as we can see on like the right, the new point is blue, and the closest to that point is the other red dot. And this in turn would classify the blue dot as the red dot since they are the closest. So an example of this, so going back to the weather example, we can apply a nearest neighbor approach in order to see how it would work out. So the white dot, again, being the new data point, is of an unknown class and has never been seen before. So looking at this as like, and using the nearest neighbor approach, which data set would this fall into? So just think about it for a few seconds. Okay, so as you can see, the closest point to the white dot would be this red dot right here. So the white dot would be classified in the same class as the red dot. So yeah, just like this. And of course, there's also issues with this model as well. So again, it's just inaccuracies within the model. So using a nearest neighbor approach is sort of just like a guess that you're assuming that the class would be like the closest class would be the most accurate, and that's not always true, as we can see in this example. However, this is an improvement from the previous technique because instead of having a fixed linear boundary, if this point was somewhere like around here, when the linear boundary might have put it onto the other class, you can see that like the nearest is like a blue point improving that accuracy of like which class it's placed into. Okay, so those two techniques are semi-effective depending on the situation, but one very important sort of technique that can be helped to make the set barrier is known as a support vector machine. So in addition to the nearest neighbor and linear regression, another approach to classification is a support vector machine. This approach uses an additional vector known as a support vector near the decision boundary to make the best decision when separating the data. So consider the data on the right. A computer uses a support vector and can draw accurate boundaries by using the assistance of existing data points. The computer will choose an optimal boundary with the best accuracy. So what does that mean? So the computer is going to look at all of the data as a whole and try to set an accurate boundary that would work best for the data set at hand. So just a way to like look at that, if we look at these three graphs at the bottom, all of these boundaries are technically accurate. They are splitting up the data points into two separate categories, but we can obviously see that this third one is the most accurate because in this case, in all of the cases actually, all the data points are following sort of like a linear line, and that linear line should be somewhere around like a parallel of the set boundary, because this boundary won't work because if there's a red point here, technically that's in the wrong class and will be classified as blue, even though the trend is following this linear pattern. So advantages of support vector machines. So another advantage to support vector machines is that nonlinear boundaries can also be drawn, such as a circle. So in all the previous examples we saw, all of the boundaries were strictly linear and just barriers between two set points. But if we have a data set like this, just like we saw in the previous example, a linear line from any direction cannot be drawn accurately in order to split the data. So the computer sees all the data and recognizes that it's more of like a cluster of red points in between all the blue points, creating like an optimal boundary to separate the two data points. Regression. So everything we just did before this was a technique of classification, which is basically that tends to split data points, where regression is using those data points to draw trend lines without drawing boundaries. So just to clarify on that, regression is a supervised learning task of a function that maps an input point to a continuous value, some real number. This differs from classification in that classification problems map an input to discrete values, such as rain or not rain. Instead of splitting classes into distinct categories, regression follows the trend of the data points. So as we can see here, this line is not trying to separate two sets of data points at all, but rather it's trying to find like a line of best fit or like an optimal trend line that follows the data in order to like solve different types of problems. So an example of where this could be useful, for example, a company might use regression to answer the question of how much money they spend on advertising and predicting the money earned in those sales. So there's no need for boundaries or categories at all for a problem like this, but we do need like a linear line. So instead of regression, regressions are used most effectively to extrapolate data from certain data sets. So what this means is instead of, again, splitting classes, what we're trying to do is follow a trend. So right now on this graph, we see the set points, but however, if the company wants to know if they put some advertising beyond where this line is going, and they want sales above where this axis is going, they can just extend the axes and look at where the line is going to follow in order to extrapolate and predict their future data points. And the same goes for a computer. If it's just trying to predict any future data points, it would use a technique such as regression. Okay. So now with regression, there's ways in order to optimize it so it's most accurate. So one technique is known as a loss function, and it's really effective.